Hello and welcome to this video on exploiting the structure of categorical variables with StructureBoost. So the first question you might ask upon hearing that title is, what is categorical structure? What do we mean by that? Well, broadly, structure is about defining similarity. So in supervised learning, you've got training data in the past, and you've got new points that you'd like to make predictions about. And essentially what you're asking is, what are situations in the past that are similar to the situation I have now that I'm trying to make a prediction about? And how can I use those similar situations in the past to make a good prediction about what's going to happen in this situation? So to motivate this further, let's think about a very simple problem where we've got a single numerical integer predictor, which is age in this case, and we're going to have a binary target variable, which is something silly, which is just, did that person buy broccoli in the last 30 days or not? So our model is just going to be the probability of broccoli given age. So it's really data sparsity which forces us to have to exploit structure. So what do I mean by that? Let's give an example. Suppose I want to make a prediction about a particular 36-year-old about the probability that they bought broccoli in the last 30 days. I look at my training data. If I had 10,000 observations of 36-year-olds in my training data, I wouldn't really need to worry about anything else. I would just take the empirical estimate, look at what's the probability given all those 36-year-olds in my data. And if, say, 2,000 of them bought broccoli, then I would know 20% is a pretty good estimate for the probability that this particular 36-year-old will buy broccoli. But now if in my training data I only had 2 observations of 36-year-olds, well, I have to do something different. I need a more sophisticated model. And whatever I do, it's probably going to look strongly at the data I have on 35 and 37-year-olds, especially if I have a lot of data on 35 and 37-year-olds. And I would say that that's what we mean by structure. Structure is the assumption that age 36 is near 35, and that in the absence of enough data on precisely 36-year-olds, 35 and 37-year-olds will be kind of the most similar situations that I have. Now note that this is an assumption. For example, if I thought broccoli purchasing depended heavily on whether your age was odd or even, then this might be a bad assumption. I might not want to look at 35 and 37-year-olds. I might want to look at, say, 34-year-olds and 38-year-olds if I thought that whether your age was odd or even is important. So when we exploit structure in numerical variables, we're making a modeling assumption. The modeling assumption is that nearby ages behave similarly, and therefore it's reasonable to average over intervals of ages. If we want to pick sets to average over, intervals make sense because they're all in one group. And one approach is to predefine intervals. So in the absence of enough data in any particular age, we make groups of ages. And you see this a lot in market research data, survey data. You'll make these groups 18 to 24, 25 to 39, and so forth. And this is a perfectly reasonable thing to do. However, one downside of this approach is that you're making those intervals without looking at the data. You're gonna, if you choose 18 to 24 and 25 to 39, you are asserting that there's going to be a step change between 24 and 25. And even if the data found that actually there's a bigger step change between 21 and 22, it wouldn't be able to do that. So an alternate approach is to let the data drive the aggregations. And if you think about it, that's really what a decision tree does. So let's talk about decision trees a little bit. Decision trees, also known as classification and regression trees, these are not used that much in isolation, but they're the foundation of random forests and gradient boosted trees. And gradient boosted trees in particular are now very common in the industry for prediction on tabular data. And packages such as XGBoost, CatBoost, like GBM, are extremely popular and used widely. So let's briefly revisit how the decision tree algorithm works. What you do is you look at each variable, in this case it's about numerical variables, and you examine every split of that variable, You evaluate the split according to some criteria. You choose the best split, you divide the data based on that split, and then you repeat that process on each child node. So here's a very simple putative data set for this broccoli problem. I've got 9 different ages represented from 18 to 67. And above, I have some data points on each as to whether they bought broccoli or not. And what a decision tree would do is perhaps look at this split and compare the data on the left versus the data on the right and see if this seems like a good split. And it would also look at a split over here and do the same thing. And in fact, in the standard implementation of a decision tree, it would check every single split allowed by this data. So in this case, since there's 9 different values of age, it would look at 8 different splits. Now, suppose instead of age, I just had some categorical variable. The typical assumption behind categorical variables is that the values are just different and unorderable, and essentially they have no structure. And the common approaches people use in dealing with categorical variables are one-hot encoding, which essentially says I'm going to try each individual variable versus all the rest of them. Those are the kinds of splits I'm going to look at. Or more recently, people have used a lot more of numerical encoding. What numerical encoding says is I'm going to impose an ordinal structure on the values of this categorical variable. So essentially, I'm going to push these down onto a line somehow. And then I'm going to treat it like the numerical variable age that we saw before. What I'd like to introduce is that there's a notion of a structured categorical variable. So for example, if these 9 values actually represented 9 different counties in the Bay Area, there would be a natural structure based on which counties border which other counties. And this might be something we would like to exploit if we thought that regionality made a difference in our target variable. We might want to explore splits, for example, of the northern counties versus the southern counties, or the coastal counties versus the inland counties, or even perhaps the wine-producing counties versus the non-wine-producing counties. So the idea is we'd want to examine partitions where each piece is a connected set of the graph. So for example, if we were using the month of the year as a variable, we might want to exploit the fact that it has this circular structure. So for example, we might want to make a split like this, where November, December, January, and February are compared versus the other months. And note that this split wouldn't be possible if we just used a simple numerical encoding with January as 1 and December as 12. Similarly, if we have US state of residence as a variable, we might want to examine a split like this. So how can we accommodate the decision tree, make it accommodate categorical variables? Well, it's actually quite simple in theory. We could just say, let's reformulate it and say for every variable, we're going to check each allowable split of that variable. And we're going to define an allowable split, meaning that it divides that structure graph into 2 connected components. And if we took this definition, numerical variables would essentially reduce to a chain graph like structure. Now, this sounds really simple and easy in practice. What are some of the challenges you run into if you actually try to do this? Well, one is that there's typically many allowable splits. Now, for a small graph like the 9-county graph of California that I showed of the Bay Area, there's only 36 allowable splits, and that's totally simple and straightforward to examine all 36 of those splits. For the months of the year, that 12-month cycle has 66 allowable splits, also totally reasonable to examine them all. However, once you get to a graph like the 48 lower states plus DC, so I call that the US 49 graph, that graph already has 4 million plus allowable splits. When you get to the 58 counties of California, you're over 100 million allowable splits. So it's going to be prohibitively time consuming to evaluate all those splits. What's even worse is that beyond being time consuming to evaluate all of them, it's even more time consuming to enumerate all of them. So just to figure out what that set of splits is that I should consider, for the US 49 graph, to get those 4+ million allowable splits and decide what they are, it required looking at 35 million connected sets and checking the complements to see if the complements were also connected. So it's easy to see we start running into problems once our graphs get a little bit too big. So how can we overcome this? Well, this is where StructureBoost comes in. And the key observation is that it's not crucial to check every allowable split. And there's some experimental results in the reference papers that I'll give at the end that show that, in fact, performance is better when we check relatively few splits. And the conjecture is that checking fewer splits serves to regularize. And this actually makes sense if you spend some time thinking about it. And there's some evidence that this is true even in the standard numerical setting, that it's not necessary to check every single possible split. And in fact, you might overfit quite a bit if you do check every single split. And if you just picked a smaller subset of splits, it would serve to regularize. And remember, what's also happening here is that because we're doing boosting, we're actually repeating this process many times over many trees. So it's not essential that we get the absolute best tree every time. So given that observation, the challenge is, can we efficiently generate a random sample of splits from this space, but without enumerating all of the allowable splits? And luckily, it turns out the answer is yes. There's one catch, is that it won't be uniform over the space of splits. So I can get a random sample from this set of splits, but some splits might be chosen more often than others. Luckily, that doesn't seem to matter too much in practice, and we still get excellent results. So I'll briefly talk about the two methods by which we can do this. How do we sample from allowable splits? StructureBoost permits two methods by which we can sample from the set of allowable splits. One is using spanning trees. So we have a graph. There are efficient algorithms to randomly choose a spanning tree of that graph. Once we have a spanning tree of that graph, removing any single edge from that spanning tree gives us a split where each side is a connected component. And after choosing the spanning tree, then we can just try every different possible edge from the tree and look at that set of splits. And we can choose multiple spanning trees if we want to get a bigger set of splits to examine. So in the spanning tree method, there's a single parameter, which is the number of spanning trees, and we're going to check every possible split that comes out of each spanning tree. The second method is using edge contraction. Edge contraction means I take an edge of the graph and I kind of squeeze the edge together until the two vertices become a single vertex. And so that reduces the size of the graph, both in terms of the number of vertices and the number of edges. I can repeat this process of choosing an edge at random and contracting it until the graph gets a small enough size. Once it's a small enough size, I can fully enumerate all the splits, all the allowable splits of the smaller graph. And the splits of those smaller graphs map very simply to splits of the bigger graph. Once I have all of the allowable splits of the smaller graph, I can randomly sample some number of those splits to evaluate. So this method has two parameters: the contraction size, how many, which essentially says I'm going to contract the graph until it reaches what size, and then the number of splits I'm going to search. After I enumerate all the splits of that smaller contracted graph, how many of them should I actually search? And I'm going through this kind of briefly. I'm going to create some more content to go into more detail on this. But hopefully this gives you a taste of how StructureBoost works, how categorical structure is meaningful and important. Thank you very much for listening. Here's some details on where you can find the StructureBoost package. here's some of the reference papers, one of which is in AI Stats 2020, the other is available on arXiv, describing categorical structure and some of the methods used in StructureBoost. Thank you very much for listening and have a great day.